as everyone finishes getting settled in, why don't you take 10 more seconds on the clicker question here. And let's see how you did on this. This is very similar to a clicker question that we had on Friday. Okay, so let's get started here. It looks like we are doing a lot better. We now have 77% getting the correct answer. We only had about 30-something% on Friday for a very similar question. So if you're not in this 77%, let's quickly go over why, in fact, this is the correct answer, 0.9 times 10 to the negative 18 joules. So I'm using the same kind of tricky language that we'd used before, not to trick you, but so that you're not tricked in the future. So if we're talking about the fourth excited state, and we talk instead about principal quantum numbers, what principal quantum number corresponds to the fourth excited state of a hydrogen atom? 5. Okay, so hopefully that cleared up for some of you why you got the wrong answer. So we know that we're in the n equals 5 state, so we can find what the binding energy is here. The ionization energy, of course, is just the negative of the binding energy. We know that binding energy is always negative. We know that ionization energy is always positive. So hopefully, putting all those things together, if you looked at this question again, we'd get 100% on it, that our only option here is 0.9, and that it's not the negative, it's the positive version, because we're talking about how much energy we have to put into the system in order to eject an electron. All right, and today we're going to mostly be talking about wave functions of electrons, but before we get to that, I wanted to review one last thing that's back onto Friday's topic, which was when we were solving the Schrodinger equation, or in fact using the solution to the Schrodinger equation for the energy, the binding energy between an electron and a nucleus. And when we talked about that, what we found was that we could actually validate our predicted binding energies by looking at the emission spectra of the hydrogen atom, which is what we did as the demo, or we could think about the absorption spectra as well. And what we predict as an energy difference between two levels, we know should correspond to the energy of light that's either emitted if we're giving off a photon, or that's absorbed if we're going to take on a photon and jump from a lower to a higher energy level. So we came up with two formulas which are similar to the two that I'm showing here. The formula tells us the frequency of the light that's emitted or absorbed based on the energy difference between the two levels that we're going between, that the electron is transitioning between. You'll notice that there's a little bit of a difference in these equations here from the ones from the other day, which is that you have this z² value in there. So these are both called Rydberg formulas for figuring out the frequency of light emitted or absorbed. And before we were looking at the Rydberg formula specifically for the hydrogen atom. And now that we have this z² term in the formula here, we're now talking about absolutely any one electron atom. And it should make sense where we got this from, because we know that the binding energy, if we're talking about a hydrogen atom, what is the binding energy equal to? Negative Rydberg over what? Yeah, so it's negative Rydberg constant over n². But if we're talking more generally about any one electron atom, now we have a more general equation for the binding energy, which has this z² term out in front of it, right? So it's negative z² times the Rydberg constant all over n². So essentially, when we're talking about these equations up here, all we're doing is talking about the regular Rydberg formulas, but instead we could go back and rederive the equation for any one electron atom, which would just mean that we put that z² term in the front. So when you solve certain types of problems, such as problems later on in the second half of your p-set, if you need to talk about the frequency of light emitted or absorbed for a one electron atom, such as lithium plus 2, for example, then you would need to plug in Z. And remember, the Z value for lithium would just be 3. The Z value for hydrogen, of course, is 1, and that's why this term falls out of that equation when we're talking specifically about the hydrogen atom. So just to finish our review of what we talked about on Friday, when we're thinking about transitions between two different states, and we're talking about a situation where the final state, the n final, is greater than the n initial, in this case, are we talking about absorption or are we talking about emission? Hearing a little bit of a mix here. In fact, we're talking about absorption. When n final is greater than n initial, we start at this lower energy state and go up. That means we need to absorb a photon. We have to take in energy. Specifically, we have to take in this exact amount of energy in order to bump the electron up to the higher energy level. So that means that when instead we start high and go low, we're dealing with emission, where we have excess energy that the electron's giving off, and that energy is going to be equal to the energy of the photon that is released. And of course, through our equations, we know how to get from energy to frequency or to wavelength of the photon that we're talking about.